All right, well, good morning. Welcome to another Monday morning. We are pushing our way here through calculus, and today's plan, we're going to do a little bit more implicit differentiation just to help you guys get the feel for that. And then we're going to turn our attention to exponential functions and logarithmic functions, kind of rounding out our knowledge of derivatives. So that's our plan for today. But before we go there, I know that there's homework due tonight, so I'm guessing that there are probably some that we want to take a look at. So any homeworks we want to look at?
It's not exactly pertaining to the problem, but it was the one that was like the marginal cost.
Okay.
And then I think I only typed in one answer, so I'm not sure if your system counted it wrong because I only typed in one answer. And I didn't type in both.
Well, without looking at your specific one, I can't answer that question. But my guess is that if it did ask for two different answers, but you only gave it one, it's probably not going to give you full credit.
Okay.
But like I said, without looking at your specific one, I can't really answer that, Susanna.
Okay. Thank you.
Oh, yeah, you're welcome. Did that problem go okay, though? You understood?
Yeah, I think I solved it right. I just remember seeing it like a yellow check mark, and I was like, oh, I wonder if it was supposed to be the other answer.
I don't know that I've ever seen a yellow check mark, so I'm not certain even what that
Oh, it's
means.
yellow. It's just like you get like half or something.
Okay.
Or partial.
Well, that's probably it. It probably did want multiple answers, and you just put in the one. So.
And then some of the
Nope,
some of the derivative ones, like the f prime, I think it's because I got it wrong because I put the square or the cube sign. I think I messaged you and then you messaged me back, but I put the square. I think I either put it after the x when I wanted it in the middle, or I put it in the middle when I wanted it after the x.
Yeah, and that is something when you enter. I know exactly what you're talking about, Susanna. And so for the rest of you, so you know what we're talking about, it's when you have something like the derivative of tangent, right? And you want to have secant squared. The thing about the computer is you enter it differently than how you would write it out. So let me actually show you
how I was supposed to type it.
Yeah, let me show you guys what that's supposed to look like. Well, let's see. Yeah, let me go ahead and share my screen here. Although my stylus isn't working right now. Let me see if I can get it to reboot. There we go. Okay. So let's say you wanted to type in, say, a secant squared of x, right? So the way that you would type this into the calculator, or into the computer, I mean, so you'd have a parenthesis, secant, parenthesis, x, close parenthesis, caret for your power, 2. So anytime you want to have a trig function that's being raised to a power, you need to put that entire trig function in parentheses before raising it to that power. So if you were just to type, say, this, the computer is going to read that as secant of x squared, which is a very different thing than secant squared of x. So my suggestion is use lots of parentheses. Put parentheses around, excuse me, everything that's inside the trig function. So like, let's say we wanted to do secant squared of 3x plus 1 or something like that. Do parenthesis, secant, parenthesis, 3x plus 1, parenthesis, close your secant, square, right? The other thing is always, you can always preview your answer, right? They always show you what it looks like. And so make sure that any powers and whatnot are not being applied to just what's inside the trig function. because that's going to be significantly different. So hopefully that makes a little more sense in terms of entering those things. But unfortunately, computers don't do math quite the same way that we do. Someday, I'm sure we'll get to a point where you can just write this in, and the computer's going to scan it and read it and put it in properly, but we're not quite there yet. Anyway. All right, so there's that one. Any other questions on the homeworks? So I'm going to take that silence as derivatives are actually going pretty well. Is that true? Are we feeling pretty good about derivatives?
Oh yeah, the other thing that I think it's just a similar issue of how I typed it in. I'm not sure if you responded, but it was multiple problems where my final answer was like 3 tangent 7x secant 7x to the 7th or whatever. And then I would convert the tangent and secant to like sine and cosine. That way I don't have like a long, like a really lengthy answer. That way I just have a fraction of sine and cosine. And then I think the system just also deducted that.
I did reply. No, the issue there was the same one that we were just talking about when you had like a sine to the 7th, for example.
Yeah.
The way you put it in was sine of x to the 7th instead of sine of x to the 7th. So it was actually the same issue. But
just a parentheses?
Yeah.
Okay, because I think on one of them, I intentionally tried to leave it as like secant and tangent, and then I got it right. But then the other like 1 or 2, it like just counted it wrong.
Well, I can just tell you from what I looked at, because I can see your most recent responses and all that. And so what I looked at showed me that you were having the same issue that I was just describing.
Okay.
So
it wasn't the fractions, it was the exponent again.
It shouldn't matter. It really shouldn't matter. Now, I don't know, like, I'm not the one who made the system, right? I'm not the programmer.
Of course not.
So I don't know. I don't know that they're like, no, it has to be as secant and tangent or whatever. I don't know that. I'm just telling you mathematically, it doesn't matter. You want to make them sines and cosines, make them sines and cosines. It's equivalent.
Yeah, like on a test, you would give me the credit for.
Absolutely.
Okay.
Absolutely. Okay. But also, I hope you're hearing me, Susanna, that the issue with yours was not the sine and cosine. It was the powers were in the wrong place.
Okay, so just put parentheses next time is what I learned from this morning.
It's all about parentheses, especially when dealing with a computer, because a computer will do the order of operations. Like it will automatically follow the order of operations, and it will never interpret what you mean, right? It will never go, oh, you clearly meant this was supposed to be secant to the 7th. It doesn't think that way. It just reads it as secant x to the 7th. So realize that computers don't think, so you have to be very careful with how you tell it what to do. So and that's just that's something good to learn, like, because for all of you, I know all of you are going into the sciences of some type, otherwise you wouldn't be taking this class. And if you're going into the sciences, more likely than not, you're going to be using computers at some point in terms of not just like solving equations and all that, but actually like using computers to do something. And it's very important with programming to be very explicit with what you do and what you say, realizing that the computer is going to do exactly what you say, right? That's like one of those genie wishes that goes wrong, right? Where you say, I want my parents to do exactly what I say. And then they do only what you say, right? It's one of those kind of deals. Computers are definitely there. All right. Well, I guess if there are no more homework questions, don't forget that next set is due tonight. But it sounds like it's going pretty well. It's really procedural, right? It's like once you get it, you just get it. All right. Well, then I'm going to go ahead and switch to the whiteboard. So I'll be back with you guys in just 1 second. All right. So today, like I said, I want to review a little bit more this implicit differentiation because it is a tool that we're going to be using as we go further, and I just want you to get a little more experience with it. So let's just review what goes on with implicit differentiation. So remember the word implicit or implied means that in this case, we don't actually know the function. We don't know it, but we're going to assume that y is a function. It's just not explicitly stated as some formula. Right? Excuse me here for a second. Pardon my finger. So we're going to assume that y is a function. We just don't know what it is. So then when we differentiate, we just have to realize we're using the chain rule. So basically, if you kind of want to just break this down, turns out that the x's you just treat like normal. You just differentiate the way we've learned all these different rules. And then the y's, you differentiate like normal. You just attach on a y prime. All right. And so even though I said use the chain rule, I mean, technically that's what we're doing, but it's a little bit easier just to remember that all this is we're going to attach a y prime when differentiating the y's. Okay, so that's all that means. We're just going to go times y prime. And then once we've got that, we can do our thing. All right, so let's warm up with an example. Let's do one of these guys. And for example, let's try this. Let's say we've got an equation here that's xy plus x divided by y equals 10. All right, so there is a graph that satisfies this equation, a bunch of xy points that when you plug them in, give you truth. All right, but I want to find the slope of the tangent line at the point 4, 2. So 4, 2 is a point on this graph. You can actually see that if you take 4 and 2, plug them in for x and y, you do get truth. 4 times 2 is 8. 4 divided by 2 is 2. 8 plus 2 is 10. All right, so there's a graph. I have no clue what it looks like, but I still want to find the slope of the tangent line at that point. All right, so here's what we're going to do. We're going to differentiate both sides of this equation with respect to x. We're going to do a d dx of each side. All right, so let's do that. So we'll just take them in order. So we start with xy. So what are we going to need, or what are we going to have to do with that xy? How's that going to differentiate?
Does it become 0? I mean, does it just or like 1? Because normally if it's just like 1x and there's no exponent, then you have nothing to bring to the front. And you lose the term.
So you're right, Susanna, that x differentiated just turns into a 1. But the problem is this isn't just x, it's xy. Okay, so Mariola just said, so that's y with a question mark. I couldn't tell if that was a y squared. Okay, so is it just y? Well, to get just y, we'd actually have to start with like a y squared term to get y. Maybe we don't start with that term. How about we save that one? Let's go from the right. So let's start easy. What about the 10? What happens to the 10?
0. It's a constant.
Okay, so it's constant. It's just going to go to 0. Boom. All right, so we're going to get equals 0. All right, so I'm going to put an equals 0 over here. Okay, so what about the x divided by y? What are we going to have to do there? Oh, come on, you know what you need to do. What's screaming at you because of that form? What rule do you think we should use? Okay, so Ali just said quotient rule. Yeah, totally. It's divided by, right? Anytime you see division, you need to think, oh, well, maybe we're going to use quotient rule. So for xy, we're going to use the quotient rule. So let's set up the quotient rule over here real quick. So we've got on top x, on the bottom y. So for the quotient rule, we need both derivatives. The derivative of x is 1, right? Kind of like Susanna was talking about earlier. What's the derivative of y? All right, so a couple of you just threw in there. Thanks, Bailey and Alia. It's just y prime, right? The derivative of y is the derivative of y. We don't know what it is right now, but we know that it's a function, right? Because it's implied that y is a function. So its derivative is just its derivative. So we're going to write it as y prime. Okay, so let's do the quotient rule on this. So we're going to get 1 times y. So y minus x times y prime divided by the bottom squared. So there's the quotient rule piece. It's y minus xy prime over y squared. So notice what happened. Like I said over here with the chain rule, we attach a y prime when we differentiate y terms. Normally, the derivative of y would just be 1, but we got 1 y prime. So we just slap that on there. Now, we had to use quotient rule because we had division. We had x divided by y. We had two functions. X is a function, y equals x, and then y itself was a function, and so we had to use quotient rule. Okay, so there's that piece. So then let's get back to the x times y. What are we going to have to do there? There you go, good. A couple of you see it now. This one's going to require product rule. Because we have x times y. Even think about how we say it, right? It's x times y. As soon as you say that word times, ooh, that's product. So that one we need product rule, which, hey, I can use the same setup. I just do something different with it. I'm going to get a 1 times y, which is y, plus x times y prime. So when we differentiate both sides here with respect to x, this is what we end up with. Y plus xy prime, that was the product rule, plus y minus xy prime over y squared, that's the quotient rule, and then equals 0. That was a constant. All right, so I don't know if you remember me telling you this on Friday. Probably not, because it was like, 3 days ago. But I warned you about the xy. And I told you this is where you're going to run into problems. That's why I keep bringing it up. xy, got to remember that's actually product rule, because it's just two different functions being multiplied together. All right, so there it is. There's our relationship between y prime and x's and y's. So one thing we could do at this point then is solve it for y prime, right? Do some algebra on it to get y prime equals. But I'm not going to do that since we are given a point, since we were told, hey, let's find the derivative at the point 4, 2. Let's plug in 4, 2. So every x is going to be turned into a 4, and every y is going to be turned into a 2. All right, so let's see what we get there when we do this. So at the point 4, 2, we're going to get 2 plus 4y prime plus 2 minus 4y prime over 2 squared equals 0. And now let's solve it for y prime. So I'm going to multiply by 4 to get rid of this fraction. So we get 8 plus 16y prime plus 2 minus 4y prime equals 0. That's 10 plus 12y prime equals 0. So 12y prime equals negative 10, or y prime equals negative 10 twelfths. We can actually reduce that down, right, to minus 5, 6. So the slope of the tangent line, remember that's what we were trying to find. The slope of the tangent line at this point is minus 5, 6. So again, I have no idea what this graph looks like, but I can tell you at this point, it's got a slope of minus 5, 6. It's going down 5 over 6. So the tangent line is pointing down, the decreasing slope. So I know that about this graph at this point. And this is the power of implicit differentiation, is that we don't actually have to know what the function is. Now, this one we could have solved for y. It would have been possible to solve it for y. Multiply by y, distribute around, you get a quadratic. We could have solved it for y. And then we could have done explicit differentiation, but this is way faster. All right, so questions on this one? I'm going to show you one more example before we move on. But so far, so good. All right, so how about this? How about a higher order derivative? We haven't looked at those at all. So how about we do this? Let's find y double prime given this. Let's go relatively easy. Let's go x cubed minus y squared equals 4x. All right, so x cubed minus y squared equals 4x again. It's whatever it is. We could solve this for y and do all that, but let's not bother. Let's do this implicitly. All right, so we need a second derivative, which of course means we need to start with a first derivative. So let's do that. Let's get the first derivative just by implicit differentiation. So we'll do d dx, both sides. And let's see what we get here. So the x cubed, of course, becomes a 3x squared from the power rule. All right, the y squared, you differentiate that, you would get 2y, right? Derivative of y squared is 2y. But since y is a function, we need to use the chain rule. So we'll slap on a y prime. So the derivative of y squared is 2y times y prime. All right, and then we go to the other side, and the other side is 4x. So its derivative is just 4. So if you're comfortable with the differentiation rules, like if you're good with how to differentiate when you have x's, differentiating when you have y's is not a big deal because you just differentiate the same way. You just make sure you throw on the y prime. All right, so there is our first derivative. Now, we're going to need to differentiate again, right? Because we want a second derivative. So we could right now jump in and do another d dx of both sides. But I don't recommend we do that just yet. We are going to do that. We are going to differentiate both sides again. But before you do that, let's solve for y prime. Let's get y prime all by itself, because it's going to make it a little bit easier going forward, just in terms of the algebra and stuff. So just trust me on that. All right, so let's solve this thing for y prime. So I'm going to move some stuff around. So I get 3x squared minus 4 is equal to 2y times y prime. So y prime is equal to 3x squared minus 4 over 2y. So a little bit of quick algebra brings us right here. All right, well, now we'll take care of the fact that it's a second derivative. So if I want a second derivative, I have to differentiate the first derivative. So I'm just going to do another d dx. All right, so check out what happens now. On the left, differentiating y prime, well, it gives me y double prime. Gives me exactly what I wanted. Then on the other side, if I'm going to differentiate, this is another place where we're going to have to use quotient rule. So let's get the quotient rule set up here. On top, we've got 3x squared minus 4. On the bottom, we've got 2y. So the derivatives respectively are 6x, or 3x squared, and then 2, y prime. Right? So again, we're differentiating with respect to y, or with respect to x. So the derivative of this would normally be 2, but because y is implied to be a function, we attach a y prime. Okay, so quotient rule says we need to do all that multiply and all that good stuff. So let's start that up here on the next line up here. So we're going to get y double prime is equal to, all right, so 6x times 2y, so 12xy minus 3x squared minus 4 times 2y prime. And that's all going to be divided by the bottom squared, which is 4y squared. Okay, so there's a quotient rule on that piece. All right, so far so good. All right, now there's one more thing we're going to take care of. And that's this guy right here. Because in our formula for the second derivative is a first derivative. We don't really want that there. Basically, we want to be able to write this all in terms of the original x and y. Because kind of the whole point of this is you don't know everything about this function, but you do know a point. And so if we know that point, we could then plug it in and evaluate whatever we're looking for. Right? So like in this case, maybe we're looking for the acceleration or whatever. So I really don't want that y prime. but I'm going to be able to replace it because if you recall, come back to this line right here. We already knew what y prime equaled. Y prime was equal to 3x squared minus 4 over 2y. So I can actually replace this up here. So I can write instead y double prime is equal to 12xy minus 2 times 3x squared minus 4 times 3x squared minus 4 over 2y. So I literally just substituted in that y prime for what we found y prime to be. And now this is all only in terms of x and y. So I'm going to simplify this just a little bit. I don't want to have fractions inside of fractions. So first of all, notice that these 2's cancel. And so then to get rid of this y, I just multiply everything by y. And we end up with y double prime is equal to 12xy squared minus 3x squared minus 4 squared over 4y cubed. So if you're not really clear on that algebra, come find me during an office hour or something, and I'll help explain it. I don't want to spend the time on it right now. All right, so there's your second derivative. If we wanted to find a third derivative, well, we would now differentiate, again, both sides of this with respect to x and do it again. You want a fourth derivative, do it again, do it again, do it again. So higher order derivatives can be done implicitly as well. The only catch is anytime you run into a y prime or y double prime or something like that, you need to substitute back in. This is really why at this point I told you let's solve it for y prime, because I knew we were going to have to plug it in. If we had just started differentiating at this point, right, come back here. If we had done the whole let's differentiate both sides with respect to x, we still would have found the exact same expression for y double prime that we had up here. We still would have gotten there, but we wouldn't have had y prime to substitute in, and we would have had to find it. So we might as well find it on the way. All right, so it still would have worked out. We still would have gotten the same thing, just a little bit faster, I think, to go ahead and solve for y prime.
I have one question.
Yeah, go for it, Ollie.
I think I understand that, like, all that algebra that you skipped except for 12xy squared. How did you get that squared?
So I multiplied by y on top and bottom. And I multiplied by y because of that's the denominator here.
Oh, gotcha. Okay, there we go. Thank you.
So I distribute to both pieces. And so for this one, it gives me a y times y, which is the y squared, and then the other one, the y's cancel.
Great, thank you.
You're welcome. All right, any other questions on this one? All right, cool. So this is implicit differentiation, and we'll keep running into it. It's not going to go away, and it's really, really handy when you run into a situation like this where you have some sort of an equation, but it's not really apparent what y is equal to, or it's going to take a lot of work to get y. There is no need, right? So really just think what implicit differentiation is doing for us is it's allowing us to find derivatives without actually knowing what the function is, because it's not important, actually. What the actual function was doesn't matter here, because this relationship is enough to let us find a y prime, which then is enough to allow us to find a y double prime, and so on. So we still have information about it. We just don't know exactly what it is, right? But we've got enough information to imply something and infer some things about it and get that answer. All right, so cool. Implicit differentiation. You're going to see that this actually kind of ties in with what we're doing with logs and exponents as well. So just hold tight there. But speaking of logs and exponents, let's get their derivatives. All right, so let's start with exponential functions. So these are the ones that are written as f of x equals a to the x. So our variable is actually our exponent. So f of x is equal to a to the x. And there were some restrictions on a. Let me just remind you that a had to be positive and also not equal to 1. So if a is any positive number other than 1, it's an exponential function. So back in pre-calc, you learned about these things, back in algebra somewhere. We talked about it a little bit at the very beginning of this class when we did our like 2-day compression of an entire year of pre-calc, right? But these are exponential functions. So what we want to look at is what's the derivative of these things, right? What's the derivative of one of these functions? Well, let's actually just start with definition. Okay, let's look at the definition of the derivative and see what we can kind of gather from this. All right, so if we're going to try to find f prime, it's going to be the limit as h goes to 0 of a to the x plus h minus a to the x over h. Just purely using that definition, right? So the function evaluated x plus h minus the original function divided by h. By now, hopefully you're really familiar with this form because we do it all the time, right? The difference quotient. All right, so if we're going to try to work with this, the first thing we're going to do is we're actually going to divide out an a to the x. We can divide out an a to the x on top. So we get a to the x times a to the h minus 1 over h. Now, this step you may not be comfortable with, so let me explain it real quick. Hopefully you're cool with the 1, because if you take a to the x and you divide by a to the x, you get 1, right? Anytime you factor something out, and the only thing in that term is that factor, what you're left with is a 1. There's that. Now, it's the a to the h you may not be entirely okay with, but what we're doing here is the rules of exponents. When you divide, we subtract that exponent. So if I'm going to divide out an a to the x, I subtract x from that exponent. So x plus h minus x is just h. Or think of it as if I were to distribute and multiply these together, multiplying same basis means we add exponents, and so we'd have x plus h. So that just came from the rules of exponents. So this a to the x, it actually doesn't affect this at all because the limit is only with h's. So I can even pull that out. And I'm left with a to the x times the limit as h goes to 0 of a to the h minus 1 over h. All right, so far so good? But now the question is, what is that limit? What do we get when we take the limit as h goes to 0 of a to the h minus 1 over h? Okay, well, here's where we're going to help ourselves out a little bit by kind of going backwards. If you look at this, this still looks like a derivative kind of form, but it's a slightly different derivative form. Let me just kind of on the side here. What if we were to look at, say, f prime of 0? So I'm going to look at this thing specifically at 0. This would equal the limit as h goes to 0 of a to the 0 plus h minus a to the 0 over h. So a to the 0 plus h, well, 0 plus h is just h. I get minus a to the 0. But hopefully you remember with exponents, if you raise to the 0, you always get 1. That's just minus 1 over h. Which coincidentally is exactly what we had over here in this limit. And so what we're seeing here is that f prime of x is equal to a to the x times f prime of 0. So I just want you to kind of pause for a second and look at this. This is kind of interesting. F prime of 0 is a number, right? It's the slope of the tangent line to this graph at 0. So it's just a number. But look at what we've already figured out. Exponential functions, their derivatives are just constant multiples of themselves. What? Let me rewrite this in kind of a different notation. Like what this just showed us is that y prime is equal to some constant. Let me call it c. I'll call it c. Y prime is equal to some constant times y. Whoa, that's kind of cool. That the only difference between this function, this exponential function, and its derivative is a constant multiple. So we're not even getting like a new function. Like think about everything else we differentiated. Sine turned into cosine. X squared turned into 2x. Right? It fundamentally changed. The form of the derivative is fundamentally different than the function itself, but not for exponentials. For exponential functions, they're really the same thing, just off by a scalar multiple. Wow, that's kind of cool. So really the question is, how do we figure out what that derivative at 0 is? All right, well, that's actually kind of a difficult thing with where we are. So let me help you out just a little bit with a specific function and what its derivative at 0 is. So of all the different exponential functions we could pick, I'm going to look at e to the x. So you remember e to the x? That's like a legit question. You guys remember e? Thumbs up if you did. If not, maybe you can give me a clap of the other reaction.
Doesn't it cancel out with natural log? Or
Okay, so E is the one that's the opposite of natural log. All right, so I'm seeing a couple of claps that you're not entirely sure. So let me just remind you real quick about E. So there is this number E. And it's around, well, okay, no, it starts 2.71828, and then I'm going to put the 3 dots because, like pi, it goes on forever. It never repeats. Right? It's an irrational number. It's even more special. It's something we call a transcendental number, but it's irrational. So it never repeats, never terminates, just goes on forever. All right, the way that it's actually defined this is equal to the limit. And now we haven't talked about these kind of limits, but we can kind of get there. But it's the limit as x goes to infinity, not to e, goes to infinity of 1 plus 1 over x to the x. All right, so we've never talked about going towards infinity, but I think you can kind of get an idea of what that means. We're just going to keep putting in bigger and bigger and bigger numbers for x. And as we do that, this number, this limit starts approaching a value. That value is 2.71828, blah, 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 blah. So like E has been known for a long, long time. Let me just give you a little history. The Babylonians, Mesopotamia, present day like Iraq area, those folks long time ago had an understanding of E. They didn't call it E. The name E, we use E because it's called Euler's number, and Euler, E-U-L-E-R, is a German name, Euler. That's why it's pronounced that way. He was a Swiss mathematician, and this number was named in his honor. So that's why it's a little e. But anyway, the naming of it and calling it E is only a couple hundred years old. But the concept of E is like a couple thousand years old, because these folks were they were businessmen, they were traders, and they looked at compound interest. And they realized that compound interest, you got more if you compounded interest more frequently. What I mean by that is instead of doing interest once a year, maybe you do it once a month. Or instead of once a month, what about once a week? What about once a day and all that? As you do that, as you compound your interest faster and faster and faster, more frequently, you do get more, but it limits, it levels off. And so they saw that there was this limiting value. Well, that was E. E is totally in there. You may remember from pre-calc doing compound interest stuff, and there was the PERT formula, A equals P E to the RT. It's not coincidence. But anyway, so they knew about E. They knew about this limiting value. And so it's kind of a special number. And it's so special that e to the x is kind of like, it's the main exponential function in math. And it does correspond with natural log. I think it was Susanna earlier said, doesn't e do something with natural log? And we'll talk about that in a second. Anyway, so we're going to look at E. Now, E, if we look at f of x equals e to the x, so what's cool about this one, and I'm just going to tell you right now, that if you were to play around with this, and go to the limit definition, right? Go to this limit as h goes to 0 of e to the h minus 1 over h. What you're going to see is that this goes to 1. Okay, and like I'm saying, you can see this when evaluating the limit. So if you look at that limit numerically, right, plug in values, you'll see that this gets closer and closer and closer to 1. All right, but I'm just going to tell you flat out, this does equal 1. All right, so then if we go to this statement, what we saw with the f prime, that tells us then that if f of x is equal to e to the x, then f prime of x is going to equal e to the x times f prime of 0. But like I told you, that derivative is 1. So we get e to the x times 1 or e to the x. And I don't know if you just saw what happened. If we were actually in person, I might be able to read on your faces and see if anybody got it. But check this out. Our function was e to the x. What's its derivative?
E to the x.
E to the x itself. This function is so freaking awesome. E to the x, its derivative is itself. This is the easiest thing ever in the world to differentiate. You don't do anything, you just rewrite it. All right, so this is kind of a big deal. This guy, e to the x, it's a super, super important function, but we've got it. F of x is equal to e to the x. F prime is equal to e to the x. I'm just going to put them together, put them in a box. We'll even make that box red. Put a couple stars by it because it's that important. All right, so e to the x is a function whose derivative is itself. That doesn't happen very often. There are very few functions that do that. You have seen one other function that does that. Can you think of another function whose derivative is itself that we've seen? So I know you're probably going through your lists and you're thinking about, okay, what about the trig functions and power functions and all that. Let me just tell you that this is kind of a nothing function. It's one that you don't even really think is a function. Yeah, there you go. Ollie got my little pun there. I said it was a nothing function. It's y equals 0. F of x equals 0. Because constants, their derivatives are 0. So you have seen another function that does this, that its derivative is itself. But it really is a nothing function. It's a boring function. Nobody cares about y equals 0. This is the first function of substance whose derivative is itself. And it turns out that all of the other functions that do that are just multiples of e to the x, or e to the x minus 2 e to the x, things like that. Those are the only functions whose derivatives are themselves. All right, well, there you go. There is the derivative of e to the x. So if we want to differentiate e to the x, it's just itself. If it's got stuff inside of it, we use the chain rule. If there's stuff being multiplied to it, we use the product rule. I mean, you can just add this to the list of things you know how to differentiate. So let me just show you real quick with a chain rule kind of thing. Like, what if we had instead y is equal to e to the x squared? So this would require a chain rule. Let me actually write it out with the Leibniz notation. We'll do a u substitution deal. So we would say, let's let u equal 2x, or sorry, x squared. So this looks like y equals e to the u. So dy dx is going to equal dy du times du dx. So dy du is e to the u. The derivative of e to the u is e to the u. Du dx, the derivative of x squared is 2x. So we get that y prime then is equal to 2x e to the x squared. Right? So if we started with y equals e to the x squared, y prime equals 2x e to the x squared. So chain rule, derivative of the outside is itself times the derivative of the inside, the 2x. So you're going to really like e to the x because its derivative is just itself. Okay, so then what about the other bases? Like what if we have 2 to the x, or 10 to the x, or pi to the x, or insert favorite a? Now, you can probably see then that it's going to be kind of similar. Like when we actually worked through it, remember we saw that a prime was equal to a multiple of a to the x. So we're going to get the same function, but times something else. So the question is, what is that something else? Well, it turns out that we can use e to the x to find them. So let's go to a generic a to the x. Now, what I'm going to do is I'm going to turn this into an e. I'm going to turn this into an e in the following way. So a, we want to think about it this way. A is equal to e to the natural log of a. Natural log is the logarithmic function that goes with e to the x. Logarithmic functions are the inverses of e to the x. Remember we talked about that? So e to the natural log of a just equals a. All right, well, let me substitute that in. So we get y equals e to the natural log of a raised to the x. And then by the rules of exponents, since I'm raising to a power, I can actually just multiply those together, those exponents together. So I get y equals e to the natural log of a times x. So y equals a to the x is the same as y equals e to the natural log of a times x. Those are mathematically equivalent. All right, well, the reason I did that is now I can differentiate. And I can differentiate using the chain rule, just like we did over here. So what I'm going to do is I'm going to let u equal the natural log of a times x. So that now we've got y equals e to the u. So I can differentiate that pretty easily. Right? So dy dx, again, is going to equal dy du times du dx. And the dy du is just e to the u, always. Again, you're going to love e's. That's just e to the u. So the question is, what about du dx? Can I differentiate this guy right here? And the answer to that is absolutely. The natural log of a is a constant. It's just a constant. So it's a constant multiple. So we're going to get natural log of a. And then I need to multiply that by the derivative of x. The derivative of x is just 1. That's 1. So this derivative is just natural log of a. So we'll go ahead and put this down here. All right, so the e to the u, I can put that u back in. That's e to the natural log of a times x times natural log of a. So there is the derivative of a to the x. But in this form, it's a little bit ugly still. So let's do one more thing. This e to the natural log of a times x, you may remember that. We saw that up here, right? That's actually just our original function, which was a to the x. So if y is equal to a to the x, then y prime is equal to natural log of a times a to the x. So let's go ahead and put that in a box, because that's how we differentiate any exponential function, no matter what the base. So remember when we were doing it at the very, very beginning, when we first started looking at what is the derivative, we saw that the derivative of an exponential function was a multiple of the exponential function. Well, there it is. It's a multiple of the exponential. It's just now we know what that multiple always is. It's the natural log of a. And you can see that this works for e to the x. For e to the x, we get the natural log of e. And the rules of log say that if you take the natural log of the base, or if you take the log of the base, you just get 1. And so it still works out. All right. So basically what this does then is allow us to get any old exponential function's derivative. So here you go. Ready? Let's say we've got y equals 2 to the x. Then y prime is the natural log of 2 times 2 to the x. Done. How about if we have y equals 1/37 to the x? Then y prime is the natural log of 1/37 times 1/37 to the x. Like, it literally is that easy. So all you got to do is rewrite what you started with and multiply it by the natural log of the base.
Can I ask a question about the very start there on the top left?
Sure.
I'm just checking, is that just you like running the hook like you were explaining before?
Not really. It's more using the inverse properties of logs. So remember with just in general, if you do f of f inverse of x, you get out x, right? So when you compose inverses, you get what you plugged in. And so I'm using the fact that e to the x, like, let's call that guy f. Then f inverse is the natural log of x. That's kind of the whole point of logarithms, is the inverses. And so if I compose these, that's putting the natural log into the exponent. And so what we get is e to the natural log of x is equal to x. And then I just put a in for x. So does that make a little more sense, Alia? All right, got the thumbs up. Cool. Yeah, I'm just using the inverse properties of these guys. All right, well, there you go. Any exponential function now, you can differentiate. And if there's other stuff with it, do the other stuff. Do the product rule, do the quotient rule, do the chain rule, do the whatever. But now when e's show up, when you get a 2 to the x because you're looking at a bacteria population or whatever, now we know what to do. Now we know how to differentiate. All right, so there's one more group of functions that you can now differentiate. Obviously, if we are talking exponential functions, we should probably talk logarithmic functions since they're the same thing, right? Like when Alia just said about the run in the hook, remember my idea of, or my analogy of the fronts versus backs of money, right? That logs and exponents are really the same thing. We're just looking at it from the other side. Well, if we can differentiate exponentials, we should be able to differentiate logs. So let's see if we can do that. All right, well, since e to the x was super nice, let's look at natural log of x. Let's look at that inverse and see if we can find its derivative. All right, give me 1 second. I'm going to adjust my shade so I don't have this super big bright spot. I traded it for a much smaller bright spot from my light. All right. So let's start here. We're going to try to find the derivative of natural log of x. So here's our goal. We're going to have a box here where we're going to put in our f prime of x. All right. Actually, let me write it down here under the glare. So we're going to figure out what the derivative of natural log is. Now, to do this, we're going to use the fact that it's the inverse of e to the x. So hopefully you remember last week when we looked at derivatives of inverses. If not, I'm going to remind you here real quick. Right? We saw that if you wanted the derivative of the inverse, it was equal to 1 over the derivative of the function evaluated at the inverse. So hopefully that kind of rings a bell. Yeah? No? Maybe? So we saw this. We saw that the slopes were reciprocals of each other, and that was because of the nature of swapping the x's and the y's. Right? So we definitely know that. All right. So here's what we're going to do. Let's think of the function that we know is e to the x. So f inverse is natural log of x. So we're trying to find the derivative of the natural log. Okay, so let's think about what we need to do then. The derivative of the natural log, it's going to be 1 over f prime evaluated at f inverse? Well, if f is e to the x, then f prime is e to the x. We know e to the x is its own derivative. So we're going to take e to the x and we're going to evaluate it at f inverse. So literally, I took the formula that we developed last week for inverses, and I'm putting in the respective functions. I'm letting f be e to the x, f inverse be natural log. So notice everywhere there was a f inverse, I put natural log. And the f prime, well, is the derivative of e, which is right here. So I know that the derivative of natural log is going to be 1 over e to the natural log of x. But we can simplify that a bit. Let's use our rules of logs. And this is actually the same rule that we did just a minute ago. The one that Ollie was asking me about. Because what happens when we compose e and natural log? They cancel each other out. So all we're left with, once we evaluate that e and log, is just x. That's the good old inverse property of logarithms. Let me move all this over here. All right, so here's what we just found out. Is that if y is equal to the natural log of x, y prime is equal to 1 over x. So let's put that in a box. Also with a couple stars. And there you go. There's the derivative of natural log. Okay, it's not as nice as e to the x, but it's not bad. Like, seriously, all it is just 1 over x? Yeah, that's all it is. It's kind of cool. Surprising probably as well, right? Like, if e to the x, its derivative is itself, and this is just the flip side, you should expect that maybe its derivative is something of itself, but it's not. It's just 1 over x. It's not really a complicated function, it's just 1 over x. All right, so why is it 1 over x? Well, because everything we've proven up to this point drives it. Let me just pause for a second and just give you this. I don't know if you kind of caught this about math, but math is always just sort of, we start at this sort of basic level, and then we add to it, and then we add to it, and then we add to it, we add to it, we add to it. But we always use those previous things. Like, think about what we've done in calculus. We started with limits, but then we used the limits to start showing derivatives. And then we use those to start showing rules for derivatives. And then we use those rules to find derivatives of other things. Like, think about when we found the derivative of tangent. We made it as sine over cosine. Oh, that's something we established way back down in trig. And then we use the quotient rule. Well, we established that just a little bit ago to find now the derivative of tangent, right? So we just always keep dumping on using what we've already learned. And this is another good example. We found this derivative using, well, what we proved about inverses, but also using rules of logarithms and all this other stuff from before. So it's never going away, folks. The stuff you learned before is never going away. And this is a big difference between math and a lot of other things, right? Like, let's say, literature. You don't necessarily have to know about how other books play out when you read Pride and Prejudice. Right? It could be helpful if you've read some Jane Austen and you can kind of compare it and whatnot. But to read Pride and Prejudice and understand it and get the story and everything, you don't have to have all the stuff before it. But to get calculus, to understand exactly what this is coming from, requires all those previous things. And you never know which thing it's going to be. So just some advice when you're learning math, try to remember as much as you can. Don't discount any of it because you never know when that one piece is coming back. Anyway, I'm starting to preach and I don't mean to do that. So let's just play with some of these. So here's the derivative of natural log. All right, well, how about the derivative of this function then? What if we've got f of x equals the natural log of 3x to the fourth plus 2x? So to differentiate this one, again, we need the chain rule. So let's think about how the chain rule works. We differentiate the outer function. So we're going to differentiate natural log. The derivative of natural log is going to be 1 over what's inside. But then we need to multiply that by the derivative of what's inside. So this will be 12x cubed plus 2. So the derivative of the natural log of 3x to the fourth plus 2x is 12x cubed plus 2 over 3x to the fourth plus 2x. Done. Here's another one. Let's take g of x. Let's make it be the natural log of sine of x. All right, so we want its derivative, again, chain rule, because we've got sine inside of the natural log. So we're going to get 1 over what's inside. So 1 over sine of x times the derivative of what's inside. So what was the derivative of sine? Just for a little refresher.
Cosine.
Yeah, that's cosine. So this ends up being cosine. So we get cosine of x over sine of x. Yeah, let's do something with that. What's cosine over sine? Which trig function is that?
Cotangent.
Good, it's cotangent. All right, so there you go. The derivative of natural log of sine of x is cotangent. All right, and so on and so forth. But I want you to notice that there's a pattern going on here. If we ever have y equals natural log of stuff, right? Whatever that stuff is, just call it u. Then y prime equals, let's see if you can spot the pattern. So here was the first one. Here was the second one. So the first pattern I want you to see is that we got a fraction both times. So there's going to be a fraction here. What goes on the bottom? All right, good. Thanks, Ollie. She just put in the chat box u, right? Whatever was inside went on the bottom. 3x to the fourth plus 2x went on the bottom. Sine of x went on the bottom. So this guy u is always going to go on the bottom. And what was the top? Good, Bailey. U prime. So this is the general derivative of natural log. So if you ever have natural log of stuff, it's really fast. Put that stuff on the bottom and put the derivative of the stuff on top. And I apologize for getting really math technical there. Like I try not to use words like stuff and things because there's a lot of there's a lot behind that. So I apologize for getting really mathy there. That was a joke. But anyway, so you just take the derivative of the stuff, put it on top of the original stuff, and you're done. So natural logs are pretty easy because there's a nice pattern. Always the same when we get it. All right, well, there's natural log. But what about the other bases? Like what if we have log base 2 or the common log base 10 or something else? What are those derivatives? Okay, well, we're going to do that to be complete. Just like we did with the exponentials, we started with e to the x and then we got to a to the x's. So let's do that. But to do those, I need to remind you of the change of base formula. And it may have been a while since you've seen this. You may not have ever seen this, but this is what we call the change of base formula. And what it does is it allows us to rewrite logs in terms of any other base that we want. All right, and how this plays out is if you have log base a of x, no, log base a of, yeah, we can call it x. You can turn it into any other base you want. So we can call it log base b using this formula right here. So this is yet another one of the many rules of logs that we teach you along the way. It's called the change of base formula. All right, so a and b are whatever bases you want, but you can always rewrite any base log in terms of any other base just by using this formula. All right, so if you've seen it, cool. If you don't remember it, that's fine. If you've never seen it, that's also fine as long as you trust me that this works. If you don't trust me that that works, again, come to my office hour sometime and I'll show it to you. It's actually not a terrible proof, but it just uses the rules of exponents. Anyway, we're going to use the change of base formula because if I have log base a, let's call it y equals log base a of x, what I'm going to do is I'm going to rewrite that using the change of base formula, but I'm going to change it into natural logs. So this is the natural log of x over the natural log of a. Okay, so just look at this change of base formula. I'm just using my base to be e. So log base e is natural log. Okay, so are we good with what I just did there? I'm getting a couple of thumbs up. Okay, cool. All right, so this is what I want to differentiate then, right? I'm trying to find the derivative of log base a. So let's differentiate this guy. So we're going to get y prime. But the question is, what do we get on the other side? Well, let's start with this natural log of a on the bottom. That's a constant, right? You tell me what base we started with, base 10, this is natural log of 10. Log base 2, this is natural log of 2, whatever. It's just a number. So it's a constant, which means when it's differentiated, constant multiples stick around. So we're still going to get 1 over the natural log of a. And then we're going to get the derivative of natural log of x. Well, we just calculated that. We just found that. So what's the derivative of natural log of x?
One over x.
Good, 1 over x. All right, so here you go. If we've got y equals log base a of x, then y prime is 1 over x times the natural log of a. So you can go ahead and put a box around that, because there is your calculate the log or the derivative of any log, any base. So let me just show you a couple. They're not really that exciting, but let's try this one. So let's say we've got f of x equals log base 2 of x. All right, so here's the derivative. We're going to get 1 over x, because of that, times the natural log of 2. Yay. Or here's another one. Let's say we've got g of x equals log of x. So g prime is going to be 1 over x times, ooh, what's the base of that? What's the base of just plain old log?
X times natural log of a. Right?
Not natural log of a, there's no a down here.
Oh, wait, just x?
All right, so Ollie just got, oh, a bunch of you just started throwing it in there. It's 10, base 10. If we just write log, it's implied that it's base 10. So there's going to be 1 over x times the natural log of 10. Right, this is mathematical shorthand. This is equal to log base 10 of x. We never write log base 10. We just write log. So like on your calculator, if you see a button that says log base 10. Just like ln is always log base e. Okay, so in this situation, that one's it's just log base 10. So this becomes 1 over x times the natural log of 10. So as long as you know what this base is, it's no big deal. The same thing if there's stuff inside. We do the same thing where we put the derivative of the stuff on top. The only difference is this natural log business. All right, well, I just want to show you one more thing. Go back to what we saw with the a to the x, right? So here was our log base a. If we had y was equal to a to the x, we saw y prime was equal to natural log of a times a to the x, right? That's what we saw earlier today. And I just want you to notice that there's definitely some similarity here. Each time we're multiplying by the natural log of a. It's just with the exponentials that's being multiplied on the top, and with logs it's being multiplied on the bottom. Now we're getting at the same thing on, opposite sides, right? We're starting to see the connections between them even in their derivatives. All right, well, there you go. There's now the derivative of logarithms. So let's add that to our library, to our list of functions we know how to differentiate. So let's just sort of recap where we are now. You know how to differentiate any kind of polynomial, because that's just a bunch of power rules. You know how to differentiate radicals, roots. You know how to deal with roots. You know how to deal with rational functions, fractions. You know how to deal with trig functions, all of the trig functions. We now know how to deal with exponentials, logarithms, inverse trig functions. Remember we ran into those, we saw, we can calculate those derivatives. So we've got the inverse trig functions. And then of course, any kind of combination of those. Because we've got product rule, so multiply random stuff together, we got it. Quotient rule, random stuff, it doesn't matter, we got it. Compose them, we got it. Like, I mean, think about it. We now have tons of stuff that we can differentiate. And just about everything that you've ever run into, we now know how to differentiate, which is big, which is really big. All right, well, I'm going to call it here. I know that we have a little bit of time left, but definitely not enough to get into what I want to do next. And what we're going to do on Wednesday is we're going to keep talking about logs and exponents, because I'm going to show you this trick called logarithmic differentiation, which is going to make it way easier to differentiate big, horrible, gnarly things by making use of the rules of logs. All right, so that's what we're going to do next time. At least that's what we're going to start with next time. And then, of course, we're going to continue on. But just realize we are going to practice a little bit more with logs. All right, so just a reminder real quick, there is homework that is due tonight. So make sure you get in there and finish that stuff by midnight. I believe it's everything up to the section before implicit differentiation. So implicit differentiation isn't due yet. But you can definitely start working on it, just like you could start working on the logs and exponents stuff. But anyway, so that's where we are. Anything else from you guys before we call it a day? All right, well, hearing none, I'm going to go ahead and stop our recording then.